Unlike synthetic problems, which I've likened to an international itinerary, a flight with stops in various cities along the way, just the isolable intermediates, mechanistic problems are really about the nitty-gritty details. It's directions, how to walk somewhere, and you need to give all of the directions along the way in order for someone to get to where they're going. So if I were to instruct, say, my parents who are from out of town how to get to the YMCA downtown, I might say, hey, first thing you do is you go out of this building, down to the parking lot, hang a right on St. Clair Street, which is to say walk west until you get to Pulteney Street, hang a right, which is to say north until you get to Washington, hang a left on Washington until you get to Norwood, hang a right, and then the YMCA will be on your left. Again, all of the little detailed steps that are necessary to get someone from where they're starting to where they need to be. That's what a mechanism is. So for mechanism problem 4 on the Miller handout, what we're specifically trying to do is we're trying to justify why we make both diastereomers of this methyl ether product when we're starting with a single enantiomer of an alkyl bromide. So this methyl cyclopentyl bromine species is a single enantiomer, and in the presence of methanol, we end up running some kind of reaction. Now, I hope you recognize that because this is a polar protic solvent, this is going to be an SN1 type reaction. You could also learn that from the stereochemistry is destroyed, making what amounts to, in this case, a 50-50 mix of diastereomers. But this must be an SN1 reaction. Again, recognize that from the stereochemistry, recognize that from the methanol, recognize that from the secondary nature of this. It doesn't really matter. So now we just need to write out the actual steps that get us there. So first, we will show the bromide taking its electrons with it and leaving. This is going to be a equilibrium step, and what it's going to do is form a cation, namely that one. It will also generate Br-, which will be floating around nearby. Now what? We also have some methanol floating around nearby, and methanol contains some electrons. If the Br- adds back in, we go back to where we came from. Therefore, we're going to do something different. At this point, you might be tempted to deprotonate this H, but there's nothing nearby that can do it. Br- is not a base. It is the counterion of one of the strongest acids we know, so it cannot deprotonate this. Methanol, even though it is a bad nucleophile, must be the thing that's serving as the nucleophile. It must be the thing that adds. It will add, possibly from the top or possibly from the bottom. Either way, the outcome is going to be that you form now a protonated species. I'm drawing this as a squiggle because the methanol can attack either from the bottom or from the top. And what you're going to form is this protonated species. Now that we have this protonated species present, then in order to finish off this mechanism, all we must do is simply remove the proton. Some common errors that I see here would be arrows that look like this. And the problem with this idea is that you're showing that the hydrogen is leaving, but that misunderstands what these arrows are. These arrows show the movement of electrons. Never ever draw this. This is not an atom movement arrow. This is an electron flow arrow. Electron flow arrows always start at a source of electron density, namely the oxygen, and they go to a place that is delta plus, namely this hydrogen. You are making a bond between the oxygen and the hydrogen that will then cause the bond between this hydrogen and this oxygen to break, pushing the electrons from that bond onto that oxygen. In other words, we are now going to be in one last equilibrium step at both of these products. Likewise, this process here would have been an equilibrium step as well. There's just an equilibrium that exists between these two. This is the correct answer for this problem, but notice, and here are some of the details that will get people tripped up, you always need to have the arrows originating at a thing that has a lot of electron density and ending where electron density is missing. You need to have equilibrium arrows where appropriate. You need to have charges on substrates as appropriate. And it's also a good idea to write down, for bookkeeping's sake, what's left over after the reaction is done. So what we will end up making is this protonated methanol species, and the other counterion will be the Br-. For bookkeeping's sake, this is what you're trying to do. I will also highlight that one way you can tell if things are going wrong is if charge is not conserved in the elementary step. So here, the bromide leaves, but this was initially neutral structure. Therefore, I'm going to generate both a plus charge structure and a minus charge structure as a result. When this falls apart, I make both the plus and the minus. When the methanol, a neutral, attacks the plus, I must end up with a plus. When the methanol, a neutral, attacks the plus, I must end up with the plus. The Br- was not involved in the second step. It was simply spectating, so it's just kind of along for the ride. These are the mechanistic details that you need to pay attention to. That's what you're trying to do in a mechanistic problem. Explain how to get from here to there from someone who's out of town.